As the pointer. Okay, so today I will talk about how we work on 3D printing, which is another fabrication technique where we employ the third dimension, like in the previous very nice presentation. We have a different approach to this. I will try to frame what we do also comparing to what has been presented before. This is a brief outline of the presentation. I will introduce the technique that we use for the fabrication, which is what we call Two Photon Lithography. And then I will talk about the on-fiber devices that we present, which is one of the strengths of our group, so where we present more original work, but we also present devices not really based on fiber, but still related to imaging. I will talk to you also about that. First part, the technique. This technique is 3D printing. In a way, this is different from what we saw before because in our case, we use a technique which is called in general like additive manufacturing. So in the previous case, you have seen light introducing, changing the material, and then removal of the material created the three-dimensional structure. In our case, we do the opposite. And we build with building blocks the full structure, and this is done by basically using photoresin, which is a mixture of a photoinitiator and monomer. And when photoinitiator is excited by light, you start a cross-linking, local cross-linking, which induces polymerization, which move from a liquid phase to a solid phase material in a localized, spatially localized way. This is what has been used as a photolithography technique for several years. The novelty of the technique that we exploit is that we use, instead of using UV light, which excites the photoinitiator, we use a near-infrared femtosecond laser, not as powerful as the one needed to change the local property of glass, but still high enough to allow to have an excitation of the photoinitiator from the ground state to the excited state, which normally would happen with a single photon in the UV. In our case, this happened with excitation of two photons in the near IR. This introduces a nonlinearity on the effect, which also you can see here in the absorption. While you focus a laser into the material, you have an absorption property, which probability, which is high enough to induce a local polymerization just on the very tiny focal volume of the laser beam. So basically, you have a way with this to induce while with UV, if you focus light like this, you have a polymerization all over the double cone of the focusing light. In our case, using two photons, you just induce polymerization here, so in the middle of the photoresin. And this, of course, this is an effect that you probably know as a two-photon phenomenon in fluorescence. Like in this case, you see that when you have a single photon of the excitation, you see fluorescence all over the part of the beam, while here you have only excitation of fluorescence in the focal volume if you have a two-photon fluorescence. This is an effect seen through fluorescence. In our case, we don't see fluorescence, we just induce polymerization. So what happened is that we create a local building block, which is typically on the size of a few hundred nanometers, 300, 400 nanometers in the lateral side, and about a micron in the vertical side. So it's an ellipsoid. And this is basically the building block, because what we do is just scanning the laser into the photoresin, you create three-dimensional structure. At the end of the process, using a proper solvent, you remove the unpolymerized material and you obtain the final structure. The material we use, and this is the different compared to the previous presentation, we use polymers, so we don't have glass. To do this, in the past we were using custom setup. Now there are commercial systems which allow us to focus really on the design of the structure, because they provide recipes where you have material, so photoresin and parameter for the laser, for the excitation are very well engineered, and so you can build relatively very fast, and the technique is improving relatively large structures. So this is the technique, and then based on this technique, we create optical structure. This technique actually has been used to create several types of structure, not only optical structure. People use this for creating scaffolds for growing 3D cell culture or other application, micromechanical system, and so forth. We have a focus on optics and creating optical system, and in particular, we have a focus on creating optical system on the fiber end. And what is the rationale for that? The rationale for that is to be able to create modular structure, because the more you have, the more function you can implement. And because the optical fiber is this very nice device that we know, which is able to carry the light from one point to the next one, is very tiny, so can be used for application like endoscopy, micro-endoscopy, so can really open the door to several investigations. But at the end of the fiber, you have your almost Gaussian beam, or you can complicate a bit the beam, but what you can do is limited if you don't create structure at the end of the fiber. So the goal is to be able to expand the capability of what you can do with the fiber by creating miniaturized optical system, because if you don't remain to the scale of the fiber, you negate the miniaturization allowed by the fiber. So you need to really retain this. 3D print is good because you use the third dimension. So it is really going you can continue the geometry of the fiber, and you can implement several very different structures. Is one-step fabrication the technique that we use. So you just typically print in situ. So you start from the fiber and you grow the structure on top of it. Next, very important thing, you create different elements, but it can be created in a single fabrication step. So the alignment is not a concern. So it's automatically aligned, even though if you have different elements that need coupling between them. So far, this approach was limited by the fact that the palette of available building block was limited. So people were demonstrated the scaling down of typical optical elements like micro lenses, micro mirror, microprisms, that I mean, just very well known on the micro scale, just scale it down to the micro scale. Or the fractive optical element, then you create phase element that can create structural beam and so forth. But we can do more on this, and we can expand the palette. And this is what we have done recently, and by introducing a new building block, which is a waveguide type of element. This is based on what we call photonic crystal fiber design. What is a photonic crystal fiber? As you probably know, a photonic, in general, an optical fiber is a glass rod where you have a refractive index created inside by some doping, some effect. And an increased refractive index is what traps the light inside of the fiber and guide the light. But about 20 years ago, people have presented this idea of the photonic crystal fiber, where you have, instead you have a single material, so you don't need, in general, to perform any doping of the material, but you create an array of longitudinal holes. So basically, this pattern of hole goes all the way to the length of the fiber, with some defects in the structure, in the whole pattern, where the light gets trapped. And this is an effect that was explained by different mechanisms. There are likely, I won't go into detail of this, but the interesting thing is that in this very nice review work recently, you can see how this idea has branched in many different structures with very different properties, because this kind of fiber allow you also to create very special properties that are not possible with the normal optical fiber, like super high birefringence, or very tiny core with very high nonlinear refractive index for the fiber, so very high nonlinear effect, and so forth. And the interesting thing is that you can tune, you can control this property by designing this pattern of hole of the fiber. Okay, so this is a geometrical handle, very powerful, by which you can control. So how people create this type of fiber is a process well known for several years. Been known. They usually use glass capillary. They put together to create a bundle. They create basically a micro-scale version of this pattern. And then they put this in a furnace, which basically melt the glass, and they pull this, and this becomes a very tiny glass, which somehow, but not very precisely, mimic the original pattern that you created at the micro scale. So it's very complex process. You need to do many repeats, and then not all geometry are possible, and so on. So the idea that we came up with is to use this technique that I presented before to create this type of fiber, or short segment of this type of fiber. And indeed, what we have shown recently, as you see here in this figure, we have basically created fiber with very different geometry of the holes, with different mechanism of propagation and trapping of light, using this fabrication approach. And we were able to get to the desired geometry in a single step. So without many repeats, many iteration steps. And some are very complex and require also very high precision on the geometrical accuracy of the pattern. So it is a technique which really can meet the requirement for this kind of fabrication fiber. Of course, the building block is very small. So what you can fabricate is not extremely big, because the smaller the building block, the longer the fabrication time will be. And then there are other technical concerns related to the machine. But for sure, this can be improved in the future. At the moment, we are able to fabricate a segment of a length of a millimeter, probably 2-3 millimeters. This is the scale of the. So it's not a fiber of kilometer, like, you know, but this is enough for creating optical element on the fiber end. Because what we do with this is we exploit the waveguide to change the shape of light at the out of the fiber to implement function. One of the things that we have presented, for instance, is a polarization beam splitter based on this concept. Very quickly, why is it interesting this? Because, as I said before, photonic crystal fiber have especially high property compared to normal fiber. For instance, the birefringence of a photonic crystal fiber, of course, it should be a photonic crystal fiber with a core which is elongated, because you need to introduce some birefringent by geometry in the structure. So this is basically the core of the fiber, is where there are no holes, and this is elliptical, and this introduces no linearity. But this is one order of magnitude higher than what you can create with conventional fibers, standard fiber. So this allows to create photonic crystal polarizing beam splitter, which is much shorter than what you can create with that is commercially available with standard optical fibers. In particular, to create a polarizing beam splitter, you need a dual core birefringent fiber. I will show you a little bit in the next slide. What is interesting, what has attracted us on developing this, is that we found that people were interested in this property, but nobody has ever presented a device based on this. People, we found several, I mean, the different design, and all are dual core. Typically, where you see A and B are the two core, because the two core are basically is a coupled system of two waveguides, birefringent waveguide, which induce at some point a change of trapping of. Basically, you segregate one polarization, one core, and the other polarization at the second core at the right length of the structure, and you implement this polarization beam splitter. The good thing of this design that can be less than a millimeter, while normal commercial systems are typically of the length of centimeter or more. But again, this complexity of this structure, so typically hole of different size or different shape, elliptical hole, are all critical point for the traditional way to fabricate photonic crystal fiber. So not a polarizing beam splitter based on photonic crystal fiber was ever fabricated. We presented for the first time a working device based on this, using this 3D printing method. And this is basically also, as you see here, is a modular structure, because the structure that I shown before here were just the part which created the splitting between the two polarization. But if you want to use this in on a real system, you need to couple this onto a fiber, and then the two split polarization has to be recovered to be coupled to the next part of the optical system, maybe other waveguides, other optical fiber. And nobody was caring about this because it was complex. While with this approach, we can do everything in a single design, in a single fabrication step, and very easily. So in this case, the dual core element here, which is this one, which replicates one of the design that I showed before, basically uses two cores which are very close together and a few micron distant and are the type of size of about a micron, the single core. Why? You know that probably you will know that a standard single mode fiber has a core of about 8 microns, something like that. So first of all, you need to shrink the beam size to couple just one of the two cores. You need a taper. Then you need to couple only one of the two cores. So you need a precise alignment that will be very difficult if you create the parts separately and you join them. While here we create a single step, so it's very easily to align. And at the out of the structure, the two polarizations are split. And then we have a fan out where you separate them and you create the beam, you prepare the beam for the next step of the process. So I won't go into much detail now of the single element. You can check on publication. But the focal point here that this structure is fabricated in situ on the fiber, is fabricated in a single step, is typically very short on the length of about 200 micron, because we implement also this coupling structure, but while the central part is about a little bit more than 100 micron. And you can control very well the optical property of this through the design of the geometry of the holes of this fiber. And all these elements have a design based on photonic crystal fiber. You see this array of holes around a core and so forth. This is the fabricated structure where you can see how well we have replicated the designed elements. So on the left side, you have a rendering of the structure where you see that the general beam with general polarization enter, and then the two polarization are split out of it. This is the structure where we fabricate only half of the structure, just to show the internal part, and you see how well these tiny structure are resolved, are fabricated. And as you notice here, there is a small offset of the structure because we need to couple just one of the core and not the two core together. And this is automatically implemented by the meter. So this is the demonstration of the device, which has a very broad bandwidth, about 100 nanometer around the typical wavelength for optical telecommunication. You can see here that where the system is in its working band, you can see that horizontal polarization, vertical polarization are very well segregated to the two cores. This is the very first polarization display based on photonic crystal fiber ever presented. The next device that I want to show you is the generation of structured beam, in particular Bessel beam. In this case, just a brief introduction. What is Bessel beam? Bessel beam are very interesting beam because of property that I will talk to you later. But in terms of mathematical description, they're basically created by a cone of plane waves that interferes. And with proper phase, you can either have, if they all have the same phase, you can have what we call the Zeroth-order Bessel beam, where a central peak and several rings around. Why, if you introduce, and here, this is the mathematical expression of this. So the Zeroth-order Bessel beam is basically a Bessel function in terms of field amplitude. With no phase, because I equal to L equal to 0 in this case. While starting from 1 and above with L, we introduce topological chart, and so the plane wave have each a different phase, which varies azimuthally, and depending on how many 2 pi of phase you create, you have first order, second order, and so forth. And what happens is that your beam has a singularity in the middle, so no longer a central peak. You have a 0 intensity point, and the ring which changes its size depending on the topological chart. This topological chart is what you probably know as optical angular momentum of the light. And in general, also a good way to describe this beam is through the Fourier transform, optical Fourier transform of this beam, which is basically a ring in terms of intensity. This is also one of the ways to generate them. I will talk to you a little bit about this later. But what are the interesting properties of this beam? One is to be diffraction-free or quasi-diffraction free, which means that if you compare a Gaussian beam with the same size of the spot versus a Bessel beam, the Bessel beam will have a much longer distance over which this side of the spot is maintained. So you can have what we call very good depth of focus if you do in some application. Another interesting property is the capability of self-healing. So if you find an object in the beam path, this can recreate itself after this obstacle. which is very interesting in many applications, for imaging, for instance, where you have scattered material and so forth. So people have tried to miniaturize the generation of this beam with optical fiber, but all the approaches presented in the literature have limitations. Typical are multi-step fabrication, so you need to join different type of fiber. Some of the fiber you need to join are customized fiber, like in this case that are ring core fibers. And because the limitation of the fabrication, typically you have a limited control on the characteristic of the structure you can fabricate, and also in terms limitation the characteristic of the Bessel beam you can generate. So the control of what is the beam size and so forth. In particular, to testify the limitation of the previous approach, no one has ever demonstrated the high order Bessel beam generation from optical fibers. So the beam which carry also optical angular momentum. So what we present in this direction is another 3D structure, 3D printed structure, where we, in this case, have a more hybrid structure. We have used our idea as a building block of a waveguide with photonic crystal fiber design, plus more traditional but miniaturized elements like refractive lenses, like a lens. And this basically implements one of the ways to see the Bessel beam, because if you create a ring beam and then you apply a lens for a Fourier transform, you get the Bessel beam, is the reverse, the anti-Fourier transform of what I showed before. So what we do here, we start with a single mode fiber, we prepare the beam with a taper, and then we enter a structure where we start with a solid core, but then this structure quickly transforms, and we can control very well this transformation of the structure with the 3D printing with high resolution from a single core to an annular core structure. I will show you a little bit better later. At the end of the structure, you have you start from a Gaussian beam, you have an annular beam, and then you have a fiber, you have a lens which implement the Fourier transform, and you have the Bessel beam. So this is typically the output of the structure, but basically we start from a solid core and we expand the structure. So the size of the hole depends on the length of the structure. So just fabricating different length of the structure, we realize ring beams of different diameter very easily with very simple say design to this. And if we don't apply any orbital angular momentum to the beam, we obtain a zero-order Bessel beam. And we have been able to generate Bessel beam with very different, very well-controlled side of the center spot and the fraction-free length, just very easily controlling the geometry of the output structure. What has been very interesting is that we have been able for the first time to have a structure which can also impart an azimuthal phase, so orbital angular momentum to the beam, because if at the output of the structure where we have annular beam, we create what we call the spiral phase plate, which is a phase place element which adds an azimuthal phase. Then we are able really to generate, and after this, there is still the micro lens, which has not been shown, fabricated here just for imaging, to show you what the structure at the output of the annular parts. But after the lens, you can really create Bessel beam. You see the ring beams, and with topological chart, we have stopped at 20, but we could go further, which is a quite high value, and considering that nobody was able before to generate Bessel beam with orbital angular momentum with an optical fiber was a remarkable result with our approach. Again, this is the first demonstration, and interestingly, because we can tune so well the optical property, we are able to control and create, for instance, two beams with the same diameter but very different topological chart, because you can change the diameter of the annular beam, the focal length, whatever, but with very simple geometrical control, you can achieve this type of result. The third application for this kind of structure is fiber optical tweezers. As you probably know, optical tweezer is a device which typically implemented with optical microscope with high numerical aperture objective, because the key point is that you need a high intensity, a gradient of intensity of the beam, which create what we call gradient forces, which are basically exploited, but because the dielectric particles are typically extracted by the high intensity part of the beam. And this has been presented several years ago. And typically, again, A configuration requires bulky element, laser, lenses, then you need an an objective for optical microscope with high numerical aperture, which typically are the downside of having a very short working distance, which creates some problem. So typical, and then requires alignment and typically can be expensive. So this is another case where people have thought, okay, let's miniaturize this with optical fiber. Let's create a system where you can implement is an integrated system, so no alignment needed, and miniaturize it. Also in this case, people are working on this, presented some solution also from our group. We have presented solution in the past, but with some limitation, okay? So again, in this case, sometimes multi-step fabrication, limited degree of freedom, lack of flexibility in some aspect. So there was the need to have a new design that was able to allow to do very simple design of the optical property and very simple fabrication, single step. This is our solution that we have presented. Also in this case, you see it is a modular structure, different element, that can look complex, but it's not complexity, is more enabling to do more, to control more into the beam, because again, it's single step fabrication. And again, we have from the fiber, we have a taper. Then again, we have a similar structure that we've seen before, where from a Gaussian beam, we generate an annular beam. And here, because we need a very large beam to have a very high numerical aperture, then we have added this new structure which works with the principle of total internal reflection. We have two total internal reflection, which allow us to expand very quickly the beam. So while here we need to be adiabatic, so we can expand only very slowly, here we can expand more quickly. And at the end, we have a reflective structure which make the beam output of the structure to be crossing at some point with very high angle, which means also high numerical aperture, and this become the tracking point. Again, all these parts can be very easily designed, can be very easily controlled, and with this control, we can control very well to a degree that was not possible before the characteristic of this structure, this optical tweezer. This is the fabricated structure. The fiber, again, is a single-step fabrication. And here is the characterization of the optical property. So you start to have, from a Gaussian beam, you have an annular beam here, and then become a very large beam from 10 micron, become hundreds of micron, but we can also control and get much larger depending just on the position where we put the second reflector of this structure. We can have a larger structure. By the way, this is not just a reflector, it's a parabolic reflector because collimate the beam which outputs from this. And then this prism basically deflect the light, and by changing the angle of this, you can change the numerical aperture, the working distance of this trapping point. So you have full degree of freedom on control of the optical property. And this is the fabricated structure. And here is a movie where we show some particles that are flown by a pipette. And you see that when particle find the spot, get trapped, then some other particle comes and kick this off, and another particle, these are small bead, 5 micron bead. You can see how strong, because there is a flow here going, so, but there is a strong trapping from the beam. Okay, well, then we have characterized the property, and because we can control the angle, we control the numerical aperture. When done some experiment to show that this indeed is the case, we can vary the numerical aperture on trapping and so on. Next step is an optical system for multico fiber nonlinear micro-endoscopy. In this case, the problem was that if you have a multi-core fiber, which is a very interesting approach to endoscopy, where you have an array of fibers, array of core. What happens is that if you apply a lens to image this on the sample, because of this array, you create a Fourier transform and you have these multiple peaks. But if you do nonlinear microscopy, this is not good because you want to have just intensity in a single spot to generate a single focus. So people have thought to change it from a regular array to a more irregular array. So this what we call aperiodic Fermat spiral multicore fiber. And indeed, if you do this after a lens, you see a single spot, some stuff around, but much more confined than before. The problem is that still with this approach, only 1% of the light get into this spot because most of the light is go to other mode. So what we have to is to apply a principle of astronomy that was called also pupil densification or hypertelescope. Basically, what you do is to expand the light out of the core of a single fiber to fill the pupil, because typically you have the fiber, which hangs here, and then a lens which focuses on the center. Here we have added an intermediate step, adding individual micro lenses which collimate the light out of single in the core, which are these lenses here. And you see that they basically very well align with the different core of this periodic pattern of the multi-spiral core. And this, in this case, 3D print is very important to be able to create in a very precise but not regular way these lenses. And then this is the full structure where we have also the final lens. And with this approach, we have obtained a 35-fold increase on the power on the desired spot on the focus, which is very important for nonlinear endoscopy, where you know the more power you concentrate in a point, the higher will be the efficiency of the process. Then last part will be for a couple of non-fiber applications, but still related to imaging. The first one is the correction of aberration green lenses for micro-endoscopy. As you probably know, green graded index optics are the thinnest objectives that are typically used for live animal imaging with cellular resolution that can be below 0.5 millimeter in diameter. What is the problem? The problem of these devices is that they have aberration. So, which means that if you move away from the center of the field of view, the quality of the image degrades very quickly, and this is more evident for longer green lenses, which means that if you want to do subcortical imaging, so you need relatively long green lenses, you are more affected by this effect, by this aberration, and so you suffer from this. And neuroscience is all about network of neurons, so the more you see in focus well, and the better for your investigation. So it was very important to achieve a better a correction for that. And typical experiments are like this, where you have a mice, and then basically you have a device, these green lenses, you open an aperture on the skull, and you insert these green lenses in the skull and penetrate at the desired depth inside the brain. And then through an optical microscope, you scan the proximal side, and then the green lens will act as a relay, and then you scan the distal side, so inside of the brain. And so on your imaging system, you will see the neurons that are imaged. So in this case, you see that there is aberration. So only the central part of the beam unfocused, while if you move away, you see some aberration. This is the rendering, but I will show you better image later. So what we have done is to design a lens, which of course has to be the most general lens possible. So use non-spherical lens is what we call freeform lens, with using VMAX, so a CAD to design an optical design software, which has designed the optimal structure which corrected for the aberration of the specific green lens. And as you can see here, these lenses were able to indeed, as you see, the red number are for the distance from the center of field of view where the quality of the beam is still good. And you see here that for different lengths of these lenses, we have different performance, but in general, with the correction of the lenses, you greatly increase the size of the field of view where you have optimal performances. And how we have implemented this? Basically, we have created a system where we glued from one side on a cover glass, on one side the green lenses, the green optical element, and on the other side, and aligning with this, we have these micro lenses. So this system can be used as a handle to introduce this in the opening on the skull, and then can be fixed in position for further investigation. You can see here how really the field of view of neurons can be increased by this approach, and you see more neurons, and so you can study more interaction between them with this approach. And very interestingly, now we have also results compared to what we have published, new results yet not published, but we can expand of 2.5 times the field of view also with 9 millimeter long green lenses, so we can go even deeper into the brain. Next final application will be counterpropagating beams track. So what are counterpropagating beams? As I showed before, optical tweezers typically use this high numerical aperture objective, which a single beam focuses the light. But there is another approach where you use two low numerical aperture objectives, and you have two beam counterpropagating, and the forces basically balance each other, so the particle cannot go in this direction. Then are focused in the transverse direction. You still have a gradient which traps the particle. This has several advantages compared to the first case, because you can use low numerical aperture objective. You have typically a larger volume of trapping, so let you to trap larger particle. And also you can apply stretches, because if you apply high power, you can apply stretch, so you can study some mechanical properties of the cell. There are two approaches to implement this. Either two optical objectives, which means also two optical systems with very complex alignment. You see, this is a typical system, it's not typical your typical microscope. So it's complex handling of the system, which bulky and alignment, or two optical fiber counterpropagate opposite to each other, with the problem that this is a static trap. Because why in this case, by using spatial line modulator or some other optical device, you can move the trap, the position of the trap, or create multiple traps. You are limited to a single trap, and so some limitation. So what we have done here is to study a geometry which could miniaturize the system and allow more degree of freedom. And indeed, what we have done is to fabricate two microprisms on a cover glass. And by using a spatial line modulator, which you typically use for optical tweezer, we create basically two sub-beams, which basically go through the system to each of the two separate prisms. And then because of the reflection, by total internal reflection or metallization of the prism, they're then at some point counter-propagating here. So with just one objective, one optical system, you can create this configuration. And so this is the theoretical setup. So you just need our device here with the prism here, and with the typical configuration for a holographic optical tweezer with a single trap, you can also move to have a counter-propagating beam. And you can do more, because you have a spatial line modulator, you can create multiple traps and manipulate them. This is indeed what in this rendering, you see what we do basically. By changing the position of the two beams, you can move the particle in the vertical direction, in the lateral direction, and also in the longitudinal direction. Just the change. And this change of the two beams is done, let's say, electronically, computationally, by changing the spatial line modulator characteristic, which is pretty common in optical tweezers, so it's nothing particularly complex. So this is what we have done in the reality, and this is, you see, a trapped particle, and by moving this is with two cameras, we can see the beam from two different focal points. You can see when we move the beam now. In this case, there is a filter, so you don't see the laser. While here you see the scattering of the laser. When we move the particle in different, you see in this case, the particle is moving in the vertical direction because it's going out of focus and in focus again. So the particle is very stably trapped, and you can be manipulated very easily. Why this is interesting? Because we can do manipulation that are not possible with a typical single objective tweezer. In particular, if you have your objective which points upward in an inverted microscope, it's very difficult. Why it's very easy to rotate particle in the plane? It's more difficult to make two particles to rotate in this direction, because the particle, or one particle, will get into the beam which trap the second particle. And so this renders complex this kind of rotation. While in our case, because we come from the side, this is possible. And you can see here, by looking from the bottom, you see two bits that we manipulate, and you see that we can make them to rotate one on top of the other very easily. And you see that one acts like a lens for the next one. Okay, again, this is a proof of principle. Why is interesting? Because what we can do is rotate. Just a moment, because I cannot cannot move my.
Maybe after this we move.
Yes, yeah, I close with it. So basically, in this case, what we can do is to rotate. You see the rotation? Because unfortunately, I cannot move my.
Not yet.
Just a moment. Some problem with my mouse. Okay, I can move this. Okay, here is a C. elegans embryo, and you can see the rotation on front of the objective, which is what you typically need for tomographic imaging, where you typically have, you reconstruct 3D particle without labeling, but just by looking to the different image taken from the particle or from the object from different angles, which is difficult to implement because you need to rotate this small object in front of an objective. While this is the system let you to do so, and you can rotate the particle and you collect the images from different angles, and this from applying this method of tomography reconstruction, phase reconstruction, you can really recreate the 3D distribution of the refractive index of the particle, which give you the three-dimensional structure label-free of the structure. Final conclusion, just to have an overview of ongoing work and general direction for this kind of research, is that we are working on expanding the concept of creating a miniaturized system on the fiber, implemented also what goes basically in the opposite direction, because meta lenses is basically whatever want to be really flat, while we want to be really 3D. But we can, the idea is that we can exploit the strength of the two worlds by putting together also the two approaches, creating modular structure which also implement meta lenses. The idea is that we can also implement in general chemical, acoustical, electrical, optomechanical parts to this not just being photonics, but also having other function, again, on the end of the fiber. Then the polymer can be a problem in some application with harsh environment, high temperature. And there is an ongoing research on how to create this kind of structure with more glass-based. So it's still additive manufacturing, but based on glass-like material, so much stronger from different environment. And we want to work, and the idea would be to expand the application for this type of approach with fiber-based device for neural stimulation or recording, or also in quantum field with collection, high numerical collection of quantum emitter, and applying this to sensor, optical communication system, and anything that can be integrated and miniaturized with optical system. These are the members of my group who have been working mainly on this topic, which much of the work is, of course, thanks to them. And thank you very much for your attention. And I'm here taking your question. Thank you very much.